Remember that differentiation just means taking the derivative. What we've done up to this point in my course is called explicit differentiation. Well, no one ever actually calls it that, but that's what we're doing. And what we're about to learn today is called implicit differentiation. And I'm going to explain how those words come into play in just a moment. But I want you to remember that dy over dx is one way to write derivative. We almost always use y prime or f prime, frankly, because it's a lot quicker than writing dy over dx, but it does mean the exact same thing. Dy over dx just means derivative. And just so you remember how to read that, dy over dx actually means the derivative of y with respect to x. And WRT is a pretty common abbreviation for with respect to, at least in math it is. So if you see WRT anywhere from here on out, it just stands for with respect to. So dy over dx can be written as, or read as derivative of y with respect to x. So just a reminder, just how this could be written. If we were taking the derivative of 4x squared plus 3x, the derivative of y is dy over dx. The derivative of 4x squared is 8x, and the derivative of 3x is 3. Or this equation over on the right-hand side is the same thing, just with t's. So this time, instead of dy dx, we would write dy dt and have that as our equation. Okay, so let's say they ask the question, find dy over dx for y equals 2x cubed minus 4x. Well, the derivative of y is dy over dx. Derivative of 2x cubed is 6x squared. Derivative of 4x is 4. Now I'm showing you this one because I want to actually show you what we're doing without ever actually showing that we do it. Technically, when we take the derivative of 6x squared, there's a dx over dx that goes with it. And when we take the derivative of 4x, there's a dx over dx that goes with that. But as you can tell, we don't have to write those because dx over dx just reduces to 1. The derivative of x with respect to x is just 1, so we never bother writing them. And I think this will make sense why I'm doing this in the next slide. But if you think about it, the derivative of y is really just 1, but we have to put dy dx with it. That's just the rule. It actually involves the chain rule, but I'm not going to get into that right now. You don't have to write the 1 here either, but my point is that technically, every time you take a derivative of anything, these pieces with d go there. It's just that when it's the derivative of x with respect to x, or the derivative of t with respect to t, it just reduces to 1 and basically cancels out, so we don't write it. Now these three functions you see here. It is explicitly defined what y is equal to. The word explicit just means it's very obvious. It's clearly spoken, clearly said, or clearly stated. So here it's clearly stated what y is equal to. It's explicit. But if you look at this first example, here we would have to say that y is implicitly defined. This still perfectly tells us how y and x relate to each other, but it doesn't explicitly tell us what y equals. It's implicit to the problem. So when it's written like this, notice it's not y equals, all the x's and y's are all mixed up, then we have to do implicit differentiation. So we just do it one piece at a time. The derivative of x squared is 2x. The derivative of 2y cubed is 6y squared dy dx. That's really the only big difference with these, and that's that you have to put dy dx with any piece that you take the derivative of that has a y. So the derivative of 4y is 4 dy dx. Even though the y went away, we took the derivative of a y, so we have to put dy dx. And then don't forget the derivative of the right side as well. The derivative of 2 is 0. So we've taken the derivative, but they asked us to find what dy dx equals. So the next thing I need to do is subtract 2x from both sides. And the reason I'm doing that is because it doesn't have a dy dx, and I'm trying to get dy dx by itself. So once I get to this step, I notice, okay, both pieces on the left-hand side have a dy dx. So I can factor out that dy over dx. that is the trick that allows you to get dy dx by itself, to just have one dy dx, and that's factoring. So then your last step is to divide both sides by negative 6y squared plus 4. And if you notice, all three of those pieces have a 2 in common, so we can just reduce that and cancel out a 2 and call this negative x over negative 3y squared plus 2. So that is the first implicit differentiation problem. And it still tells you the same thing as normal derivative. It tells you the slope of that original equation at any given point. The only difference here is not only would we need to know x to find it out, we would need to plug in x and y, since they're both part of the derivative. These are the 4 steps to all these problems. You take the derivative with respect to x, you move all the pieces with dy dx to one side, and all the pieces without dy dx to the other. Then you factor out dy dx and divide over whatever's left. So if you need to write those down or need to commit them to memory, feel free to pause right here, but I'm going to be moving on. Next one says find dy dx for y cubed plus y squared minus 5y minus x squared equals negative 4. Again, just taking one piece at a time. Our first step is to take the derivative, so we do the derivative of y cubed is 3y squared dy over dx. The derivative of y squared is 2y dy over dx. The derivative of 5y is negative 5 dy over dx. The derivative of x squared is negative 2x. The derivative of negative 4 is 0. Now I like to say that you can use Marxism or socialism to explain the next part of the problems. Okay, so bear with me. We're using the same steps I just wrote on the previous slide. First, you need to separate the haves from the have-nots, which is what Marx said the society was separated into, the haves and the have-nots. So we separate them. We have 3 terms that have dy dx and 1 term that has not dy dx. So I move the one, I'm not dividing, I move the one that does not have, the have-not, over to the other side. But socialism would tell you, well, you need to take those people who have and take away what they have. So all 3 pieces have dy dx, so we take away what they have. We take away the dy dx. And then once you've taken away what the haves have, you need to distribute it or divide it with everybody. So then you divide both sides. So I don't know if that silly story helps you or not, but that's one way you can try to remember these steps. So dy dx is equal to negative 2x over 3y squared plus 2y minus 5. Next it says find dy dx for sine of y equals x. The derivative of sine is cosine y dy dx. Always put dy dx with anything that has a y that you take the derivative of. The derivative of x is 1. Now things are already separated. The dy dx is by itself. The thing without dy dx is by itself. There's no need to factor since there's just one piece. So our only other step is divide both sides by cosine y. That gives us dy over dx equals 1 over cosine y. You can leave the answer like that, or if you remember, 1 over cosine is the same as secant. So either form of that answer is okay. Alright, last example. We have find dy over dx for x squared y minus 3y squared equals 3x cubed. What's different about this one is this term right here. We have an x squared being multiplied by a y, which means we're going to have to use the product rule. So I'm going to call f x squared and g y. F prime is 2x, g prime is dy over dx, or 1 dy over dx. So f prime times g gives me 2xy plus f times g prime. So this portion right here takes care of this portion right here using the product rule. Then the derivative of 3y squared is negative 6y dy over dx. Derivative of 3x cubed is 9x squared. Now this throws some people off because they think, wait, why does that have dy dx if it doesn't have a y? Remember, you were multiplying these two pieces together, and g did have a y, so that's why its derivative has dy dx. Now we need to separate the haves from the have-nots. So I'm going to keep the two dy dx terms where they are, and then subtract the 2xy over, because it doesn't have one, giving me x squared dy over dx minus 6y dy dx equals 9x squared minus 2xy. Then I factor out the dy dx, that's my third step. And divide both sides by x squared minus 6y. So dy over dx is equal to 9x squared minus 2xy over x squared minus 6y. And that is implicit differentiation.